All right. Good afternoon, Christine, Dan Kennedy, and Denmark. So before we start, a quick reminder. So we will have the third problem set tomorrow, November 24th. It will go live in Canvas at 8 a.m. And then the deadline is December, hold on. Kailan nga ang deadline natin? Ang deadline ay November 29. So that's going to be on Monday, right before midnight. Tama ba? Tama, no? November 24th to November 29th yung problem set natin. And the coverage would be yung limits and continuity. So yung dalawang chapters na yun. All right? Hold on. Nakapag-extra na ba tayo ng limits? Oops. Nabanggit ko na ba kung ano ang coverage niya? Nalimutan ko na kagad yung coverage. Nakapag-prop set na tayo ng limits and continuity. So basta yung coverage niya ay hanggang unit 3. So simula dun sa hindi natin na-cover sa problem set 2 hanggang sa unit 3. Okay? So hindi nakasama tong unit 4. Nakalimutan ko kung saan tayo tumigil sa problem set number 2. So, ayan, nahalata tuloy na hindi ko pa nagagawa yung problem set. I was thinking na 22 pala ngayon, tapos 23 pa bukas. So, yung pala 24 na bukas ang bilis ng panahon. So, and that only leaves us with about, I think, 4 weeks and change for the semester. So, medyo ilan na yung mga linggo na pagsasama natin. But the nice thing is that we only have 2 chapters or 2 units left for Math 155. So nandito yung unit 4, derivatives of functions in the set of real numbers, and unit 5, integrals. So, but of the two, unit 4 is much shorter kasi konsepto lang naman siya ng derivatives. And the nice thing about the derivatives that we learned in Math 36 or in elementary calculus ay siya na talaga yung konsepto ng derivatives even in a more generic treatment of the term derivatives. Hindi katulad ng limits na pwede pa nating daanan yung pagiging defined niya, not necessarily on an open interval, pero sa isang pero as long as yung kukunan mo ng limit ay yung number kung saan natin kukunin yung limit ay isang limit point ng given function f. Now, in the case of derivatives, medyo well-structured na yung discussion sa elementary calculus. So, in this unit, we will just go over some of the properties that siguro yung mga mabibigat na properties involving derivatives, and we look at the proofs of the properties na hindi natin pinrove from elementary calculus. So siguro dadaanan lang natin ano yung proof ng sum and difference rule, ng product rule, ng quotient rule, but we will focus more on the the mean value theorem, Rolle's theorem, Fermat's theorem. What else? I think we also have Darbo's theorem para sa derivative. So basically, dadaanan natin yung definition, yung mga elementary results, pero hindi na natin sila ipoprove nor i-illustrate. Mag-focus tayo dun sa mga results na either hindi nyo pa napoprove sa Math 36 o mas malaking implication niya in calculus in general. So you will see here that Unit 4 only has 2 sections, 4.1 and 4.2, so mabilisan lang talaga to. I expect I can finish this on Friday, within the week. And then we can start with integrals next week. So tapos yun na yung magiging coverage ng panghuli nating problem set. So it's going to be Unit 4 and Unit 5 for problem set number 4. Oh, by the way, I already uploaded Unit 4 dun sa Google Drive folder natin, accessible using the link on Canvas. Kaya lang I made some last-minute edits. Siguro mga 3:57 ko na-upload yung final version, the version that I'm using right now. I found some major typos, so hinabol ko talaga na i-correct sila. So if you downloaded Unit 4 over the weekend or until kani-kanina, so paki-read download itong bagong version. Okay? So let's start and go over the material. So of course, we'll begin with the definition of the derivative. And you will see here na walang pinagkaiba yung definition 4.1 from the definition that you have seen in elementary calculus classes. So if we look at it more closely, so we can see that the function f is defined on some subset of the set of real numbers. No mention of any interval. Pero pag i-define ko na yung derivative at a point A, all right, may preamble na dapat una si f ay defined on some open interval I, which is a subset of A containing A. So, and then this is part of the if and only if statement. So it's not a simple preamble to the definition. So, kapag kasi function f ay hindi defined sa isang open interval containing A that is included in the domain, so there's no point of talking about differentiability kasi hindi na kagad siya differentiable based on the definition we are given here in 4.1. So even if the function f is defined on an arbitrary subset A of the set of real numbers, dapat para makapag-usap tayo about the derivative at a number A in the domain, dapat si function f ay defined sa isang open interval containing A. All right? So, and then dapat defined din si f kay A. So, hindi pwedeng kay A lang siya defined or kung wala kang maliit na open interval kung saan mo ma-define yung function all throughout that interval. Okay? Now, once you have gone through that requirement, all right, pwede ka nang pumunta dun sa limit definition ng f prime. F prime at x is the limit of f of x minus f of a all over x minus a as x approaches a. Or hold on, let me see. Okay, so there's a typo here. Nakalusot pa sa akin. This should be f prime of a. So the derivative of f, denoted by f prime, evaluated at the number a, is equal to the limit of the divided difference. So ang tawag natin dito ay divided difference para hindi ko na lang uulit-ulitin yung pagbasa dun sa fraction as x approaches a. So in short, as the denominator goes to 0. Or if you want through the other, you want to use the other version, you can use an increment on the argument of f. So you can take it as the limit of f of a plus h minus f of a all over h as h approaches 0. But in either case, ang tinitingnan natin yung behavior habang yung mga x's palapit ng palapit kay a. Alright? So titingnan natin ano yung ratio o ano yung limit ng ratio ng difference between function values divided by the limit by the difference between the x values. So I hope you have seen the graphical interpretation of the derivative. This is nothing more but the slope of the tangent line passing through the curve at the point A. So kung babalikan natin, so though this should be just a review of Math 36. Okay, x, y-axis. Then if this is our function, y equals f of x. Okay, so the derivative at the number a is basically the slope of the tangent line passing through a f of a. So titingnan natin itong yung slope ng tangent line na to. So ito yung tangent line na sinasabi natin. All right? So the tangent line actually is the limit of the set of secant lines passing through A and a nearby point, say X. So tapos makikita nyo kung bakit ganoon yung pagkaka-define dun sa derivative. Bakit siya limit ng difference quotient as the number X approaches A. So pwede mo itong tingnan as you can consider secant lines, meaning secant lines is our lines passing through the curve at exactly 2 points. Okay. Halimbawa, ito si A. Kumuha ka ng isa pang point, say dito. Say, let's call it x1. Kunin mo yung function value kay x1. And then if you draw the secant line, or the line passing through, okay, f of A and f of x, f of x1. So ito yung makukuha natin. All right. But imagine what happens when the second point becomes closer and closer to the first point. So kapag ka itong pangalawang point na x1, hinigit ko na palapit ng palapit kay A, mapapansin nyo kung siya ay magiging palapit ng palapit. Oops, hold on. Okay. Kung yung line na yun ay palapit ng palapit doon sa kung kung yung function kung yung x1 palapit ng palapit kay A, yung secant line na mabubuo nyo, so makikita nyo etong point na to, hold on, yan, gumagana na siya. Yung point na to ay palapit ng palapit kay A, so yung x1 palapit ng palapit kay A, makikita nyo yung secant line ay magiging malapit na dun sa tangent line. So basically, that secant line will coincide with the tangent line, and hence the slope of the secant line will be arbitrarily close to the slope of the tangent line. Okay? Kasi pwede nyo itong tingnan. Balikan natin yung definition. Ito lamang ay slope ng line passing through x, f of x and a, f of a. So, kaya pwede natin siyang tingnan as the slope of the secant lines. Ganon din naman, kung pipili ka ng isang x2 mula dun sa kaliwa ni A. So, magiging itsura nga lang nung secant line ay ganito. Nandito yung second point. Okay. Hindi ko ma-move yung ayaw mag-work yung ginawa ko kaninang animation, pero okay, drawing ko na lang siya ulit. Okay. Okay. So kung ito yung second line, so kung habang si x sub 2 palapit ng palapit papunta kay A, so makikita natin ay hindi ko magagawa yung animation ko kanina. Palapit ng palapit pa rin yung secant line. So just use your imagination. Palapit ng palapit yung secant line doon sa tangent line. Okay? So that's why, kung makikita nyo, ganito yung pagkaka-define analytically ng derivative, even though geometrically, we know that that would be the secant line. Alright? So ang explanation niya, siya yung limit ng slope ng mga secant lines, as the second point is chosen to be closer and closer to the number A. Tapos ito yung slope ng secant line, kunin mo lang yung limit niya, ito na yung limit ng tangent line. Okay? And f prime of A, in this particular case, is called the derivative of f at the number A. Okay? So if this limit exists, so sinasabi natin that f is differentiable at the number A. Okay? Or in particular, if you want to say, or if you want to check if the function is differentiable all throughout the set, so kailangan lamang siya ay differentiable sa lahat ng elements ng set na yon. So that's what the last paragraph is saying. So yeah, that's a quick recall of the definition of the derivative that hopefully you still remember from elementary calculus. So let's look at the basic properties and some illustrations of the definition of the derivative. So in example 1, i-consider natin yung power function x to the n, where n is a natural number. And let's consider a real number a. So we want to show here, using definition 4.1, that the derivative of f at a is equal to this piecewise function. Kapag si a ay hindi equal kay 0, sure tayo na ang derivative ay n times a to the n minus 1. But if the derivative is 0, if a is 0, then the derivative is still equal to 0. Okay? So ito ay isa dun sa mga kailangan kong i-correct kanina. Late ko na realize. So bakit may exempted na case kapag si a ay not equal to 0. And let's see why here in the proof. So let's prove the first case. The first case is if a is not equal to 0. If a is not equal to 0, then we can manipulate the derivative, the expression in the definition of the derivative in a nice way. But of course, it goes without saying that hindi na nilagay dito sa example, si x to the power n ay defined for all real numbers. So therefore, it will be defined in any open interval containing a. So it makes sense to talk about the derivative at the number a. Kasi nga yung domain ni f ay lahat ng real numbers, or it's the set of all real numbers. Okay? So we know that the limit should exist. So it's just for us to show that the limit is indeed equal to n times a to the n minus 1. So we'll start with the definition. F prime of a is the limit of the divided difference. as x approaches a. And then, okay, let's just have it as x to the n minus a to the n all over x minus a. All right. So that's by substitution. F is x to the power n. F of a is a to the power n. And then if you perform the division here, the quotient will be this guy. Or if you factor x minus a from the top, you'll get x minus a times this long expression here. The x minus a's will cancel each other out, leaving us with this expression. And this is why I realized earlier na kailangan kong exempt yung case na si a ay 0 because of this term here, a to the power n minus 1. So if n is equal to 1, magkakaroon ako ng a to the 0. Pero si a ay 0, magkakaroon ako ng 0 to the 0, which is undefined. So kaya kailangan ko siyang i-exempt. All right? So, yun. And then we are now just evaluating the limit. But this guy is a polynomial, and we knew from the previous chapter that polynomials are continuous everywhere. Tapos ang idea ng continuity, analytically at least, ay equal yung limits of function value. So we can just simply plug in x equals a into this expression, and we'll get a to the power n minus 1. So here we'll have a times a to the power n minus 2. So that will be equal to a to the power n minus 1. And so on until the end. So hanggang sa dulo, we just have a bunch of a to the n minus 1s added to each other. In particular, there would be n of them. Kasi nga, mula kay power x to the n minus 1, isa na siya. Power x to the n minus 2, dalawa na siya. And so on. Pag hanggang sa dulo, so ang power, ito ay power 0. So mula sa power 0 ni x hanggang sa power n minus 1 x, we have n terms, right? So essentially, we are adding up n pieces of a to the n minus 1, and that will simplify to n times a to the power n minus 1. And that completes the proof when the case is, for the case that a is not equal to 0. The case when a is equal to 0 is much easier. Again, pupunta naman ako sa definition ng f prime of a, which is basically the limit definition. Plug in x to the n, that's x to the power n, but f of a is equal to 0 because a is equal to 0 in this case. And then this guy will be x minus 0, so giving us with a monomial x in the denominator. And then simplifying this quotient, we'll have x to the power n minus 1 as x approaches a. And again, x to the power n minus 1 is a polynomial. It is continuous. The limit is just a function value. So it's going to be 8 raised to the n minus 1. But a is equal to 0, so we'll get 0 over here. Okay? So, yeah. Parang may problema rin pala. Hold on. Kapag ka si kapag ka si n ay equal kay 1, meron pa rin pala akong problema. Magkakaroon pa rin ng 0 to the 0. Huh. Yeah, mali pala yung casing, yung pagkuha ng cases na pinili ko. Probably here I could have, hold on. Okay. That pala dito ay if n is not equal to 1. Tapos ito ay if n is equal to 1. Kasi inulit ko lang yung same mistake in the previous version of the work text of the lecture notes, yung a to the n minus 1. Yun din pala yung may encounter ko dito. Magkakaroon din ako ng a to the power n minus 1. Tama ba? Yeah, I think that would be the problem there. Okay. So, kailangan kong... Yeah. Actually, hindi ito 0. Dapat siya ay magiging 1 na ngayon. Okay. So, paki-correct nung example 4.1. I think this should be fine. Tama ba, guys? Magiging x to the 1, derivative ni x to the 1 ay x to the 0, which is just equal to 1. okay, and then evaluated at any a, that should be equal to 1. So I think this is the better, or actually this is the better correction to example 4.1. Tapos syempre mababago na tong proof na to. So yung f prime of a, so ito dapat ay n equal to 1. Ito ay n not equal to positive 1. Alright? So kapag ka si n ay equal kay 1, yung f prime of a will be x minus a all over x minus a. Then we take the limit as x approaches a. So this will just be the limit of 1 as x approaches a. That would be equal to 1. Okay? So end of proof. Yeah, sorry. Inulit ko lang pala yung same mistake with the previous case. So yeah. So ito dapat yung restriction. Okay? I hope that's fine. All right, so a quick remark here before we go to the second example. The result in example 1 can be extended to any real number n. So hindi siya restricted sa mga natural numbers as exponents. So you can use any real number for your exponent. The proof would be much more involved. Actually, yung general case na n is an element of R, ang pinakamadaling proof sa kanya ay kapag ka natapos ka ng mag-logarithmic differentiation. Pero medyo malayo pa yon. But for this particular course, we are not specifically into proving basic derivative formulas. So mas gusto natin yung mga theoretical consequences niya. Okay? So yeah, so we will skip the proof, the general proof for a real number n. Okay? Now, another illustration is example 2, pagpapakita naman na hindi differentiable ang isang function, in particular, the absolute value function at the number 0. Okay? So, in this particular case, we need to look at Okay. Inisip ko kung bakit siya nagpalit ng notation. So this could have been f. This could have been f. Okay lang naman. All right. So in order for the derivative to exist, all right, so this limit must first exist. So probably let's rewrite this. So let's check. Basically, we want to show that the limit of f of x minus f of 0 over x minus 0 as x approaches 0. And if f is the absolute value function, this would be the limit of the absolute value of x. Absolute value of 0 is 0 all over x as x approaches 0 does not exist. All right? Para mapakita na hindi siya differentiable kay 0, kailangan nating i-prove or i-argue na yung limit na to ay hindi nag-exist. Okay? Now, an important fact first, f is defined on an open interval containing x of 0. So we know that if that is the case, then we can look at the limit from the left and the limit from the right. So that means the actual limit will exist if and only if the limit coming from the right is equal to the limit coming from the left. Okay? So pwede nating tingnan ano yung nangyayari mula sa kaliwa ni x of 0, which is 0, or ano yung nangyayari mula sa kanan ni 0. Okay? Let's start from the right first. Tingnan natin yung limit ng function na ini-investigate natin as x approaches 0 from the right. For x's coming from the right of 0, yung mga x's na yun ay laging positive, right? Tinitingnan natin ano yung nangyayari mula dun sa kanan ni x. Sa kanan ni 0. Pero sa kanan ni 0, lahat ng numbers doon ay positive. So, and then the absolute value of any positive number is itself, right? Absolute value of x is equal to x if x is greater than or equal to 0. Hence, the absolute value bars will just vanish in the next step. Tapos meron tayong over 0, x over x is equal to 1, limit of 1 as x approaches 0 from the right, that's going to be equal to 1. However, when we look at the limit as x approaches 0 from the left, another typo there, okay? So limit ang absolute value of x all over x as x approaches 0 from the left. Ngayon naman, yung mga x's na kinoconsider natin ay mga negative numbers, right? Kasi nasa kaliwa nga sila ni x. And then the absolute value of a negative number is its negation, all right? Para siya ay maging positive, right? For instance, absolute value of negative 5 is the negative of negative 5, thus producing positive 5. So ang absolute value ng isang negative number x ay negative x. Kasi kung si x ay negative, yung negative x ay magiging positive. So that means this absolute value bar or this bars can go out at the cost of introducing a minus sign. So the numerator becomes negative x, denominator remains to be x, then this simplifies to negative 1. Limit of negative 1 as x approaches 0 coming from the left is equal to negative 1. The left-hand limit is negative 1. The right-hand limit is positive 1. They do not agree with each other. Therefore, the limit doesn't exist. And since this limit doesn't exist, then we can conclude that f is not differentiable at 0. Okay. So dapat mga f's yun. Okay. So that's a typical way on how to prove non-differentiability. Just a caution, we will adopt definition 4.1, pero we will not be talking about derivative from the left and derivative from the right. Sa Math 36, dumaan pa yung discussion sa derivative coming from the left and derivative coming from the right. Specifically, this is your derivative from the right. This is your derivative from the left. Pero sa Math 155, we don't care about those one-sided derivatives. Okay? So, yun lang nga lang, ang usapan dapat mag-exist yung limit from the right. But intuitively, the limit from the left and the limit from the right are actually your one-sided derivatives. But we will not be going through that, the nitty-gritty of those things kasi ang mas focus natin ay differentiability in general. Okay? So, okay. So just a remark. Example, okay. So in example 1, we have a continuous function x to the power n, and we have shown that it will be differentiable. Okay. But in example 2, we have seen a continuous function. Remember the continuous, the graph of the absolute value of x is just the V-shaped graph, right? But this is a continuous function, and yet it is not differentiable. So continuity doesn't necessarily imply differentiability. May mga continuous function na hindi sila differentiable. And can you guys remind me ano yung geometrical interpretation ng or ano yung parang geometrical test para na masabi ng isang function ay differentiable? Do you guys remember? Ano yung dapat wala sa graph ng function para siya ay maging differentiable?
Sir, dapat wala po bang cusp?
Yeah, that's right, CK. Thank you. So dapat walang cusp. Yung cusp ay yung mga ganito yung itsura. So it is not differentiable at this point kasi meron diyang cusp. Ano pa? Meron pang dalawa. Okay, anyone else who remembers a geometric test for differentiability? Pag nakita niyo yung graph tapos meron ito, sure kayo na hindi siya differentiable kagad. Any other volunteers?
Corners po, sir.
Okay, thank you, Rexter. That's right, corners. So bawal din yung may corners. Halimbawa, yung function nyo ay ganito. So yung absolute value. So example siya, meron siyang corner or meron siyang sudden turn. Okay? Doon sa vertex. So hindi rin siya differentiable doon. So bawal yung may corner, bawal yung may cusps. Other term for corners ay sudden turns. Okay? Ano pa yung isa? Actually, ito yung pinakamadali. Anyone? Dapat ay... Sige, masyado yatang malalim yung iniisip nyo. Dapat ay walang discontinuity. Kasi pag meron kang function na halimbawa step function, automatically, hindi na siya differentiable dito. Okay? Kasi wala siyang limit. So actually, that's the criteria for differentiability. For continuity using differentiability. But we will see that, or baliktad. Uh, criteria for non-discontinuity. Okay? So pero makikita natin yan as the converse of the next result that we will prove. Theorem 4.1 tells us that if your function is differentiable, then it is continuous at a. But we already knew from example 4.2 that the converse is not true. Continuity is not sufficient for differentiability, but the other way around is true. Differentiability is sufficient to conclude continuity. Okay? Now, okay. Ito pala, mag-insert ako ng notation. Idadagdag ko na lang sa next iteration ng notes. So notation, okay. F is differentiable at a number A in its domain. Will be written this way. So sulat natin siya na F is differentiable. So curly D at the number A. So when you see something like this, that means F is differentiable at the number A. Tapos, kung siya ay differentiable at a set, we can say F is differentiable at a set A. Or kung sa isang interval, pwede nating isulat na ganito. Okay. So F is differentiable on the open interval, or F is differentiable on the closed interval. All right? So para lang hindi mahirap isulat yung pagiging differentiable niya at a point or at a set or on a set. Okay? So parang katulad lang siya nung notation natin sa continuity. Curly C yung gamit natin sa continuity. Sa differentiability, curly D yung gagamitin natin. Okay? So basically here, what we're trying to prove is being a member of TA, or being differentiable at A, implies continuity at the number A. Right? So the trick here is to show that the limit, knowing that the limit exists, the limit of the difference quotient exists, we want to get from there a statement that the limit of f as x approaches a is equal to a. All right? So yun yung gusto nating ipakita. Right? Kung si G ay differentiable, dapat si G ay continuous. Pero para masabi na si G ay continuous, it is sufficient to show that the limit of G as x approaches A is equal to the function value. Okay? So you can analyze the proof in the usual way. Start with your assumption. Okay? Ang assumption natin si G ay differentiable at the number A. So for now, the only thing we know from differentiability is that the limit of the difference quotient exists. So alam natin itong G prime of A ay nag-exist. Tapos again, our strategy to show that G is continuous, compute natin yung limit ni G, ipakita na siya ay equal kay G of A. Right? And then here's the trick that we will be using. Instead of right away computing the limit of G, ang i-compute ko ay yung limit ni G of X minus G of A. So this is the sneaky trick used to make the proof easier. Okay? So imbes na limit ni G of X yung tingnan natin yung limit ni G of X minus G of A. Bakit ko siya gagamitin? Kasi halos kamukha na siya nung nandun sa limit definition ng derivative. Alam ko to ay nag-exist. So, titingnan ko na lamang kung paano ko siya magagamit para mapalabas yung limit ni G. Okay? So, but here we already have a G of X minus G of A. Para magamit ko yung G prime of A, kulang lang siya ng X minus A sa denominator. So I'll introduce I'll introduce an X minus A in the denominator, but to preserve equality with the previous expression, I need to reintroduce another factor X minus A, this time as a numerator. So that those two introduced factors will just cancel each other out, bringing us back to where we started. Okay? Tapos, ang kagandahan nung ginawa natin yon, alam natin ito ay nag-exist or may limit ang g of x minus g of a all over x minus a. Tapos alam din natin na yung x minus a ay may limit din siya. Alright? So when you have two existing limits, you multiply them together, we get the limit of the product, all right? So the limit of this guy exists, the limit of this guy exists, so the limit of the product is just the limit of those two guys. But what is the limit of the first factor? Ano yung limit nito? This is basically g prime of a. And then what's the limit of x minus a as x approaches a? It's a continuous linear function, so therefore the limit is just equal to 0. Okay? So yung limit ng product, alam natin yung limit ng parehas na factors ay nag-exist, equal lang siya sa product ng dalawang limits. But this is g prime of a times 0, we'll get something equal to 0. Okay? And then a simple algebra using the algebraic property of limits, makikita natin na from here, being equal to 0, we can conclude that the limit of g as x approaches a is equal to g of a, proving that the limit of g is just the function value at a, so which is precisely the definition of continuity. Okay? So, end of proof. Okay? I think you have probably seen this in Math 36 kasi madali lang siya, pinaglaruan lang yung definition. Pero ang pinaka-tricky part dito ay paano ko naisip na computehin yung limit ni g of x minus g of a instead of computing the limit of g. Okay, ito yung mga minor, actually minsan hindi minor eh. Ito yung mga sleeky tricks na pwede niyong gamitin para mapadali yung proof ng isang statement. Okay? So from here, I would like to siguro pwede ako dito insert ng isang remark, which is basically the converse of theorem 4.1. So if f is not continuous at the number a, then f cannot be differentiable at the number a. So this is no proof is required for this remark because this is simply the converse of theorem 4.1. So we can say here that the converse of theorem 4.1 gives a nice criterion for this for non-differentiability. Okay. So continuity implies differentiability. Yung converse niya, baliktad. Differentiability implies continuity. Yung converse niya, kung hindi siya continuous, hindi siya posibleng maging differentiable. Okay? So yun lang yung gusto kong idagdag dito sa remark. Okay? Now, Theorem 4.2 is just a listing of the algebraic properties of the derivatives. So here we have the limit of a sum, the limit of a scalar multiple, the limit of a product. So this is your good old familiar product rule. And this is basically our quotient rule, right? So yung mga proofs niya, proof ng part A, just apply the definition and it's going to be straightforward. Ganun din sa B, straightforward definition ng derivative yung gagamitin. Fa-factor out nyo lang si K. Medyo tricky yung proofs ng product at saka quotient rule. I don't remember kung pinuprove pa siya sa elementary calculus, pero ito yung process niya. Meron ka na naman trick na gagamitin. Okay. So basically, ito yung difference quotient na mag-appear dun sa derivative ng, sa definition ng derivative ng isang product, right? Function value at x minus function value at a divided by x minus a. All right. Basically, actually, almost ito na yung proof. Gawin lang nating f prime, fg prime of a equals the limit as x approaches a. Tapos dito, okay, by definition of the product of two functions, so maging f of x times g of x minus f of a times g of a all over x minus a. Siyempre, kukunin ko yung limit as x approaches a para maging equal na siya dun sa limit. And then here's the trick. Ito yung cunning trick na kailangan ko. So, kinopya ko to mula dun sa original, right? Then nag-introduce ako ng additional terms which sums up to 0 to preserve the equality with the previous expression. So limit pa rin siya, pero inintroduce ko ito. Okay? Yung sum niyan ay equal kay 0, pero ang kagandahan sa paggamit sa kanila ay ito, yung susunod na mangyayari. So I will group these two terms together and group these two terms together. If we look at the first group, we can factor out f, right? So factor out si f, matitira ay ito, and take the limit. Okay. Itong buong expression na yan. Then, ganun din yung gagawin ko sa second group. Sa second group, ang pwede ko namang i-factor ay si g of a. Alright? Factor g of a out, matitira ay ito. Okay? But what are our assumptions here? Okay, f and g are both differentiable. So kung siya ay differentiable, alam natin siya ay continuous. Pag continuous, nag-exist yung limit at yung limit ay yung function value lamang. So pag kinuha ko yung limit nitong first term, okay, ang limit ng f of x as x approaches a ay equals sa f of a kasi nga si f ay continuous. This guy, ang limit nito as x approaches a is basically what? This is the definition and derivative, right? Limit ng difference quotient. So that's g prime of a. Plus in the second term, the second group, we will have limit of g of a, but g of a is a constant. It doesn't depend on x. So siya na yung derivative ng sarili niya. Times the limit of this difference quotient. But again, that's the same form of the difference quotient that appeared in the definition of the derivative. So siya lamang ay f prime of a by definition. And there you go. You get the proof of the product rule. So again, ang crucial point dito ay mag-introduce nitong number na to that simplifies to 0. Okay? Now for the quotient rule, may similar trick din na gagamitin. You can go through the proof yourself. And yung trick ay ito. Nagdagdag siya neto. But the idea is still the same. I-group ko sila, mag-factor out ako ng appropriate constant or appropriate common factor. And then yung second factor ay isang difference quotient na pag kinuha niyo yung limit ay magiging equal lang dun sa desired derivatives. Okay? So yeah, I think we covered almost all of the derivative formulas. So sa Math 36 na lang yung pagde-derive nung derivative ng bawat function. Okay? So here we are dealing with arbitrary functions, and I will assume that you already know what the derivatives of those functions are. So pag nagpa-problem set ako dito, hindi nyo na kailangang i-prove na ang derivative ng ln x ay 1 over x o ang derivative ng sine ay cosine. So I will just assume that you already proved them in Math 36 para gagamitin na lang natin siya sa 155. Okay? Now, let's move on. We'll have Theorem 4.3, but again, this is your familiar chain rule for the derivatives. Again, in Math 36, the focus is for you to be able to apply the chain rule for functions or composition of 3 or more functions. Sa Math 155, natin siya ipoprove. Kasi nga hindi tayo magko-compute dito. Gusto nating malaman ano yung proof or bakit totoo yung chain rule. Okay? So we have the usual assumptions for the chain rule. F is a function from A to R. G is a function from B to R. And then the image under F of the set A is a subset of B. Para yung mga f of x's, pwede silang pumasok sa G. So dapat yung result under the function f ay nandun sa domain ni G. All right? So that G circle f will be well defined. And then if f is differentiable at A and G is differentiable at f of A, then G circle f is differentiable at A with this derivative. So nakita nyo na itong chain rule na to. Let's look at the proof. Okay? Now, for the proof, we want to show that this limit exists. Kasi kung mag-exist yung G circle prime of A, dapat ito yung itsura niya. Function value pero yung function natin ay g circle f. So g circle f evaluated at x minus g circle f evaluated at a. Tapos ginamit yung definition ng composition divided by x minus a. So what we want to show here is that this guy is equal to this. Yun yung gusto nating ipakita. All right? So here are some intermediate steps. Medyo meron uling medyo cunning na trick na gagamitin, pero bago tayo makarating doon, we need to iron out some of the details. Okay? So the assumption is that g is differentiable at f of a. So kung si g ay differentiable sa f of a, si f of a, remember, is just a constant. So ibig sabihin, this limit exists. Right? So ito yung g of y minus g of f of a all over y minus f of a as y approaches f of a. Kasi ang kinuha natin dito ay derivative ni g at the number f of a. Right? So ito yung difference quotient na gusto nating hanapin. And then from here, I'm gonna define the function v. Si function v ay yung expression na nandun sa loob ng limit minus g prime of f of a. Okay. But this function v is not defined when y is equal to f minus a because of exactly this guy. Wala tayong naging problema dito sa taas kasi limit yung kinukuha natin. Limit nung difference quotient as y approaches f of a. Pero dito, walang limit na involved, nagde-define tayo ng isang function. So when y is equal to f of a, we will have a very big problem here because we will have a 0 in the denominator. Thus, thus f of a is excluded from the domain of v. Pero aside from that, pag kinuha natin yung limit ni v of y as y approaches a, we will get 0. Okay? So kasi pag kinuha natin yung limit both sides, this will become g prime of f of a minus g prime of f of a, right? So essentially, pag kinuha ko yung limit as y approaches f of a, kukunin ko rin yung limit nito as y approaches f of a. The first factor simplifies to g prime of f of a, and then the second term is minus g prime of f of a. So they will essentially cancel each other out, telling us that the limit of v of y as y approaches f of a is equal to 0. Okay? Pero ang problema nga, meron tong removable discontinuity. Ang limit niya ay laging ay equal kay 0 kay f of a, pero hindi siya defined when y is equal to f of a. But that can easily be remedied by redefining it to a function d, right? Si function d ay equals sa v kung si y ay hindi equal kay f of a, pero siya ay isa-set natin to be equal to 0, which is incidentally is the limit when y is equal to f of a. And then this function d now is a continuous function. Kasi yung limit ni dy as y approaches f of a ay equal kay 0, which is actually the function value when y is equal to f of a. So nakapag-construct tayo ngayon ng isang continuous function, okay? Which in particular has limit equal to 0 as y approaches f of a. And then, ano yung susunod na mangyayari? Titingnan ko yung equation 4.1. Saan ang galing? Yung bago mag 4.1. So mula dito, ang daming dinaanan, no? Bago yung trick. So here, okay. So what I'll do here, since now I will be looking at what happens when I am interested at cases when y is not exactly equal to f of a, so I can actually manipulate this a little bit, okay? Tapos pwede kong isolve saan equals si g of y minus g of f of a. So from here, doing some algebra will give us gy minus g of f of a ay equal dito. Okay? Which is fine. So vy, mamaminosan lang siya or mapaplusan lang siya. Hold on. Ano nangyari? Tama ba yung expression? Kakaroon ng Vy, kasi ito yung sinusolve ko. Alright? So magkakaroon ng Vy plus G prime. Pero yung Vy, pwede kong palitan ng dy kasi equal lang naman siya sa Vy whenever y is not equal to f of a. So dapat siya ay magiging d of y plus g prime of f of a times y minus f of a equals g of y minus g of f of a. Right? So ito ay equals sa g prime of y plus dy. Tama ba, guys? Dapat ito ay plus. I think that should be a plus. Vy dy plus gy minus g of a all over y minus f of a. Oh yeah, that's a plus. Kasi makikita nyo dito sa susunod na example, plus yung nakalagay. Okay? So that's fine. Plus nga ito. And then we will replace y by f of x. Okay? Assuming that x is not equal to a. And then we divide both sides by x minus a. So mula dito, lahat ng y's, papalitan ko ng f of x. Tapos, i-divide ko both sides by x minus a. That will give us equation 4.1. And then we take the limit of both sides as x approaches a. Limit as x approaches a. As x approaches a, this guy is basically f circle f prime of a. Kasi derivative siya ng g circle, limit siya ng difference quotient involving g circle f. Now, on the right-hand side, limit as x approaches a, no? Ito ay constant. Ang limit nito as y approaches f of a, which happens when x approaches a. Ito ay equal kay 0. So, matitira lang ay si g prime of f of a times the limit of this guy. But this guy is exactly the derivative of f evaluated at a. So yeah, that's how it simplifies to that. And essentially that proves the chain rule. Di pala masyadong malaki yung trick na ginamit. Medyo mabusisi lang bago makarating dito sa line na ito. Okay? So I think this could have been done in math 36 pero masyadong technical yung proof. And actually, ang focus natin sa 36 ay paano mag-apply ng chain rule. Okay? So that's that. Any questions, guys? Actually, nag-usap kami ni Sir Edu, ni Sir Hatulan kagabi. Parang bored kami parehas sa konsepto ng derivatives kasi parang wala tayong halos ma-discuss sa derivatives. Mas interesting ang derivatives when you go to graduate level kasi mas mahirap i-satisfy yung differentiability kaysa integrability. But thanks to Newton and Leibniz, nagkaroon ng parang equivalence, yung derivatives at saka integrals, them being the inverse process of each other. Kaya sa undergraduate level, mas nag-work tayo sa integrals kaysa sa derivatives kasi napaka-technical yung konsepto ng derivatives. At actually, kahit nga sa graduate level, iniiwasan yung malalim na pag-discuss ng derivatives kung pwede mo naman makuha yung mga topics when you talk about integrals. Hindi mo lang siya matatakasan when you study partial differential equations, nandun talaga yung mga derivatives, pero nandadaya pa rin yung iba, instead na i-consider yung derivatives, kinukuha naman yung integral equation equivalent ng differential equations. But that's how it is. Medyo mahirap kasi yung requirement para sa differentiability. Kasi yung continuity, hindi siya sufficient para mag-conclude na siya ay differentiability. Na siya ay differentiable, pero yung continuity, sufficient siya para maging integrable. Okay? So, and sa real analysis, at saka actually kahit sa applications, ang ating mas concerned tayo sa mga continuous functions, right? Or almost all models that we are dealing with for natural phenomena, sila ay mga continuous functions. Pero pagka continuous siya, hindi ibig sabihin differentiable na siya kagad. Pero pagka siya ay continuous, automatic siya ay integrable na kagad. That's why medyo minsan neglected talaga yung konsepto ng derivatives. Yung mga nag-174 dyan, tandaan nila na napaka-unstable ng numerical differentiation. Kaya nga kaya ina-avoid din yung numerical differentiation. So, yung idea, yun yung downside ng mga derivatives. Pero the theoretical value of the derivatives should not be discounted because they give rise to very nice theorems. And I think the focus of the next few pages here in the lecture notes would be to scrutinize or to look at this very nice theoretical results. So una, yung interior extremum theorem, which is quite a mouthful if you will always refer to Theorem 4.4 that way. So I want to call it Fermat's theorems, Fermat's theorem. Though maraming theorem na nakapangalan kay Fermat, you have Fermat's last theorem, Fermat's little theorem, Fermat's theorem about two even numbers yata or two prime numbers. So maraming nakapangalan kay Fermat. Pero when in the class, at least when we talk about Fermat's theorem, we're talking about the interior extremum theorem. Okay. Parang yung ano lang, Theorem 3.7, which is our version of the extreme value theorem. Sometimes I call it the Weierstrass, or actually most of the times I call it the Weierstrass theorem. Okay. Not to be confused with Weierstrass's first approximation theorem in numerical analysis. Pero minsan mas madali silang tandaan by these names. Lalo na yung Theorem 4.4. Okay? So from now on, I will refer to Theorem 4.4 as Fermat's theorem. Pero ano yung sinasabi ng Fermat's theorem? Well, ito lang yung parang criteria natin para sa relative maximum or relative minimum. Or actually, ito yung konsepto ng critical numbers. Okay? Or bakit tayo gumagamit ng critical numbers sa optimization. So you can think of it as a necessary condition or a necessary condition for optimality. Okay? So ano ba yung sinasabi niya? So let's consider a differentiable function on the open interval AB. So that's a requirement. It says that if f attains a maximum or a minimum, actually hindi pala sinabi yung maximum kagad. Pero if f attains a maximum at a number x sub 0, all right, then f prime of x is equal to 0. F prime of x sub 0 is equal to 0. Okay. So nasabi niya lang, kung siya ay nagbigay ng relative maximum, dapat yung derivative at that point is equal to 0. And the same thing is true when f of x sub 0 gives you a minimum. Okay. So balikan natin yung graphical interpretation niya. So meron akong differentiable function, so dapat smooth siya, wala siyang cusps, wala siyang sudden turns, dapat continuous din siya. Okay. From A, B. Okay. So this is one such continuous and smooth function. So differentiable siya. And then this function attains a maximum at this number x sub 0 in the interior of the open interval AB. And it says here, or Fermat's theorem tells us na kung siya ay nagpa-maximum dun sa function, dapat ang derivative at that point x sub 0 must be equal to 0. And true enough, our geometric interpretation for the derivative of the function is the slope of the tangent line. So pag kinuha natin yung tangent line at x sub 0, ito yung makukuha natin. Okay? Ito yung limit ng mga secant lines. And here, the tangent line is horizontal, and the slope of a horizontal line is equal to 0. So at least graphically, we can imagine why Fermat's theorem is true. Okay? So, ito yung dahilan kung bakit sa Math 36, pag naghahanap tayo ng relative max at relative min, kinukuha natin yung derivative at tine-equate kay 0. Kasi Fermat's theorem says na kapag ka may maximum or minimum, dapat yung derivative ay equal kay 0. Okay? Pero hindi niya sinasabi na kapag ka ang derivative ay equal kay 0, hindi necessary na meron kang maximum or minimum. Kaya ang tawag natin sa kanila ay critical numbers lang. sila yung mga candidates para magbigay ng maximum at minimum. At sila lang yung posibleng candidates. Walang magpapa-maximum or magpapa-minimum sa isang function na hindi zero yung derivative sa kanya. And that is due to Fermat's theorem. Okay? Let's see why this is true by looking at the proof. So we will consider an intermediate point, x sub 0, of the interval AB. And then what we will do is we construct any sequence x sub n or any sequence y sub n on the open interval AB with the following conditions. Dapat si xn at saka si yn ay nagko-converge sa x sub 0. And this can be done because what? Because AB is, or actually x sub 0 being an interior point of AB is a limit point of the open interval AB. Dahil limit point siya ng open interval AB, merong sequence sa loob ni AB na nagko-converge kay x sub 0. And we can further put a restriction na i-consider ko lamang to be xn's ay yung mga mas maliliit kay x sub 0 at yung mga yn's sila naman ay mas malalaki kaysa kay x sub 0. So you can think of xn to be a sequence of numbers to the left of 0, to the left of x sub 0, while the sequence y sub n is a sequence of numbers coming from the right of x sub 0. Okay? So dahil inassume natin na kunwari si f of x sub 0 ay maximum, okay? Kung siya ay maximum, ibig sabihin yung f of x sub n minus f of x sub 0 ay less than or equal kay 0, right? Kasi nga ito yung maximum. Si xn ay nasa interval. So ibig sabihin ito ay dapat mas malaki or equal kay f of x sub n. So if I subtract these two guys with f of x sub 0 being the subtrahend, I get a non-positive difference. Okay? The same thing is true. Okay? F of x sub 0 is a maximum. Again, if I will use it as a subtrahend, this time to the minuend f of yn, it doesn't matter if the yns are to the right of x sub 0. Pag kinuha ko yung function values nila, lagi silang mas maliit or equal kay f of x sub 0. Because again, f of x sub 0 is assumed to be the maximum. So the minuend minus the largest possible value, dapat siya ay non-positive then for all n. Okay? And then now, if we take the limit, okay, kunin natin yung limit ng f of x ng difference quotient, right? Gusto ko ipakita na yung limit na to ay equal kay 0. Okay? So titingnan ko yung limit of, kasi alam ko si f ay automatically continuous, all right? So f is differentiable, so siya ay continuous. So ibig sabihin, kahit anong sequence na nagko-converge kay f of, kahit anong sequence na nagko-converge kay x sub 0, dapat yung limit ng f of x sub n ay equal sa f of x sub 0, right? So definition ng continuity in terms of sequences. So I can extend that notion into this guy. Alam ko kasi itong limit na to ay nag-exist, all right? Dahil nag-exist yung limit na yan, yung limit ng sequence, yung limit nung bagong sequence na kino-consider natin dito, the numerator being the difference between function values, all right? So alam ko ito ay negative from here, all right? So this is less than or equal to 0. The denominator is less than or equal to 0 because the x sub n's are to the left of x sub 0. So yung x sub n minus x sub 0, lahat sila ay non-positive. So we have a non-positive number divided by a non-positive number. The quotient will give us something that is positive. Okay? So yung limit ay positive, so ang f prime of x sub 0 must be greater than or equal to 0. But on the flip side, okay, pag tinignan naman natin using the sequence yn, pag kinuha natin yung difference quotient dun sa taas, okay, para dun sa derivative, makikita natin ito ay negative pa rin, again, because f of x sub 0 is the maximum. but the derivative is positive. This should have been y sub n. Okay? Dahil ang mga y sub n's ay nanggagaling sa kanan ni x sub 0, etong difference na to ay positive or equal to 0. So the numerator is non-positive, the denominator is non-negative. Non-positive divided by a non-negative number must be non-positive. So we have two statements here about f prime of x sub 0. Una, si f prime of x sub 0 ay greater than or equal to 0. On the second statement, f prime of x sub 0 is less than or equal to 0. And for these two things to happen at the same time, f prime of x sub 0 must be equal to 0 as desired. Okay? And that's the proof of Fermat's theorem. And again, thanks to Fermat's theorem, we know that the only candidates para magbigay ng relative max or relative min ay yung mga critical numbers kung saan nagiging 0 yung derivative for any differentiable function on the interval AB. May exemption nga lamang kapag hindi differentiable yung function sa x sub 0, posible pa rin siyang magbigay ng maximum or minimum. But if we are considering a function f which is differentiable on the entire interval AB, we know that the maximum and the minimum will occur at critical numbers lamang. Okay? So yeah, I think that's it. All right. I guess we are down to the last two results for today. I'll just discuss Lemma 4.1 and Darbow's theorem. But do you guys have any questions? Masyadong tahimik yung klase. But that is usual for you. Pero may tanong ba kayo, guys? If you don't have any questions, you can use the like button para lang malaman ko na nandyan pa kayo. Di ba talaga kayo nagre-react or di ko lang nakikita yung reactions? Something must be wrong with my connection. But I hope you guys are good and still there. Or info overload na ba kagad? Or you guys are already anxious about the problem set tomorrow? Okay. So, all right. So I'll assume that everything is fine unless you will tell me otherwise. Okay. Now, Lemma 4.1, there is a major typo here. Na-correct ko na to dun sa latest version. But if you guys, again, are using the previous version, kindly correct this. Okay. And this guy. Ano yung sinasabi ng Lemma 4.1? So kapag ka si G ay differentiable sa closed interval AB, tapos yung derivative ni G kay A at derivative ni G kay B follows this inequality. So G prime of A is less than 0 while G prime of B is greater than 0. Then there exists two numbers, x and y, on the interval AB such that G of x is smaller than G of A and G of y is smaller than G of B. Okay. So ano lang yung sinasabi ng Lemma 4.1? Kapag ka meron tayong differentiable functions sa closed interval AB, where the derivative of G prime and G prime of B are of opposite signs. Okay. So yung G prime of A ay negative, yung G prime of B ay positive, then G of A nor G of B can be absolute minima on the interval AB. Okay? So kapag ka ito raw ay totoo, si G of A at saka si G of B ay imposibleng maging absolute minima doon sa interval AB because we can always find function values that are smaller than G of A and G of B. For instance, you can find G of X that is smaller than G of A and G of Y being strictly less than G of B. So essentially, this lemma guarantees na hindi pwedeng maging minimum or maging absolute minimum si G of A at saka si G of B if this assumption is true. Okay? And this is a very important ingredient in the proof of Darbow's theorem. Okay? So yung proof ng lemma 4.1 will be left to you as an exercise. Pero ang idea lang naman dito ay gamitin yung definition ng derivative dito, yung limit definition ng derivative, tapos paglalaruan yung limit na yon. Okay? So use the fact that the limit of g prime of a is negative. Expand nyo to, magiging limit siya ng g of x minus g of a over x minus a as x approaches 0 is less than 0. And then look at what you can say about g of x and g of a, knowing well that x belongs to the open interval AB. So si x ay mas malaki kesa kay a, so this guy would be a positive number. And then look at what will happen here. Okay, is it possible that g of x is greater than or equal to g of a? I don't think that will happen because we know that the limit will be negative. And again, the denominator is known to be positive, then that's fine. And then you can argue in a similar fashion to establish the other inequality. So again, in short, bottom line ng lemma 4.1, hindi pwedeng maging minimum si g of a or si g of b. And that's what I'm going to use in the proof of Darboux's theorem. Yung Darboux's theorem, pwede nyo itong tingnan as an IVT for the derivative. Makikita nyo kung bakit. Okay. Now, what are the assumptions here? We'll consider a function f that is differentiable on the closed interval AV. Now, if alpha is a number between f prime of a and f prime of b, okay, or pwede rin naman yung pakabila, you will have an analogous proof, then there exists a number c on the open interval AB such that f prime of a is equal to alpha. Okay? So halos kamukha na to ng intermediate value theorem. Ang requirement nga lang ng intermediate value theorem, yung function involved dapat ay continuous. So kung si f prime ay continuous, pwede natin i-apply yung IVT kagad to come up with this statement. However, all we know is that f is differentiable. Kung si f ay differentiable, ang alam natin si f ay continuous. But we don't know whether f prime is continuous or not. Okay? Now, even without knowledge that f prime is continuous, the fact that f is differentiable kind of guarantee na merong intermediate value or merong version ng IVT, and that's what Darboux's theorem guarantees us. So let's look at the proof of Darboux's theorem. It is not that difficult because most of the work required for the proof was already done in lemma 4.1. Okay? Yun yung purpose ng mga lemmas kasi. So sila yung nagpapadali dun sa proof ng mga major theorems. The proof of those theorems or those lemmas could have been absorbed inside the proof of the bigger theorem, but mas elegant na nakahiwalay na lang siya. Especially if that lemma can be used for other results. Okay, so let's take advantage. Let's see how we can take advantage of that result. Tapos may trick na naman dito na gagamitin. So si f ay differentiable. So alam ko si f din ay continuous. Okay, just at the back of our minds. But I will define g, an intermediate function, to be f of x minus alpha x. Okay, makita nyo bakit out of nowhere. Bakit out of the blue, dinefine ko si g na ganito. All right. Now, we will see the utility later, but let's analyze this function g. Since f is differentiable, so that means f is differentiable. Alpha x is also differentiable because it's a polynomial. Okay. Now, the difference of two differentiable functions is again differentiable. So we say that g is differentiable on the closed interval AB. And not just that, we can use the algebraic theorem for derivatives, telling us that the derivative of difference is the difference of the derivatives. So on g prime lamang, knowing that g is equal to this, is just f prime of a minus the derivative of alpha x. So si alpha x ay may derivative na negative alpha. Okay? Now we will assume, part of the assumptions actually, is that alpha is strictly between f prime of A and f prime of B. So we can borrow this statement from our assumption, and then I can subtract alpha x. Or actually, I can subtract what? I can subtract alpha from both sides. So I'll get f prime of A minus alpha less than 0, less than dapat ito ay f prime of B minus alpha. Okay. And this guy will be what? Oh yeah, but this guy is exactly G prime of A, and this guy is exactly G prime of B. Because again, G prime is f prime of x minus alpha. So this is G prime of alpha, this is G prime of B, sorry, G prime of A and G prime of B. So we have this inequality. And this should look familiar because, okay, ito yung form na nandun sa lemma 4.1. But before we apply lemma 4.1, let's make the following observations. Kung si G ay differentiable sa closed interval AB, then we know that G is automatically continuous on AB. Dahil si G ay continuous sa isang compact set by EVT or by Weierstrass's theorem, okay, si G ay merong maximum at minimum point sa isang number dun sa closed interval AB o dun sa compact set na AB. Alright? So meron nag-exist na maximum at saka minimum value. Pero ang sinabi dito ay yung bounds, okay, kapag meron kang inequality na to, yung bounds ni A at saka ni B nung set ay imposibleng magbigay ng minimum. Yun yung sinasabi ng lemma 4.1. Since we have G prime of A and G prime of B being strictly less than and greater than 0 respectively, then by lemma 4.1, G of A and G of B cannot be absolute minima. Okay? Dahil hindi sila pwedeng maging absolute minima, therefore, there is some other point C on the interior of the closed interval AB at which G attains its minimum. Okay? So nagiging minimal si G sa isang number C sa loob ng interval AB, which is strictly greater than A and less than B. At by Fermat's theorem, yung interior extremum theorem, kapag meron kang minimum sa number C, dapat yung derivative kay number C ay equal kay 0. Okay? Now, G prime of C is equal to 0, but G prime of C is equal to f prime of C minus alpha equal to 0. And then we add alpha to both sides to get f prime of C equal to alpha as desired. Nakakita na tayo ng number na C sa pagitan ni AB, or actually hindi lang nasa pagitan, strictly nasa pagitan ni A at saka ni B, such that f prime of C is equal to alpha. And again, there's another typo here, dapat ito ay C. Okay? But that's the idea, and I hope you appreciated yung paggamit ng lemma 4.1, actually pati rin ni Fermat's theorem para sa proof ng Darbo's theorem. Okay? So the proof is, I think the proof is pretty straightforward, but that is due to the fact that it borrowed results from three major theorems: lemma 4.1, Weierstrass's theorem, and Fermat's theorem. But essentially, Darbo's theorem, as I mentioned earlier, is simply the version of the IVT for the derivative. So makita natin dito na mas strong talaga yung requirement ng differentiability kaysa sa continuity. Kasi it transcends not only the requirement that f prime be continuous for the IVT, ginagaranti niya yung existence ng number, hindi mo na kailangan yung continuity ng derivative para masabi yung conclusion ng IVT. Differentiability of f is sufficient para mahiram natin or makakuha tayo ng result which is in parallel to the IVT, which would have otherwise required f prime to be continuous. Okay? Now I think I will stop here. Next meeting, I still think that we can finish the module. This will be just some results associated to the mean value theorem. We'll start with Rolle's theorem, which is basically a specific case of the mean value theorem. Then we'll use Rolle's theorem by a simple tweaking of the function involved in Rolle's theorem to prove the mean value theorem. And then we'll generalize it a bit to get a more general mean value theorem. Okay. And probably a selected result, yung tingnan natin yung L'Hopital's rule, yung case na 0/0. So I guess this is a nice selection of results that were not tackled from a theoretical perspective in Math 36, and we'll do them in Math 155. Okay. So yeah, I think that's it. Do you guys have any questions? Or masyado bang info overload na for today? Okay, I only went too fast because I think most of the things here are already given in Math 36. Nakita niyo na sila before. So there's no much examples involved. Kasi nga yung mga theorems naman yung gusto nating i-prove. Okay? All right, so if there are no questions, then good luck to your problem set that will be live tomorrow and due on Monday. And then and I hope you enjoy the rest of the night. And guys, let's see each other again on Thursday. Okay? Bye, everyone.